This video provides an introduction to exponential functions. An exponential function is a function of the form f of x equals b to the x, where b is greater than 0 but not equal to 1. b is called the base of the exponential function. So basically, an exponential function is going to have the variable in the exponent. That variable b is going to be some kind of number. Let's practice evaluating exponential functions for a given x value. Let's evaluate f of x equals 4 to the x at x equal to 1.2. So this is the same as 4 raised to the 1.2 power, and we're just going to plug this into our calculator and then round to the nearest hundredth. When we do this, we get 5.28. Next, let's evaluate g of x equals 6 to the 3 minus x power when x is equal to 1.2. G of 1.2, that's going to be equal to 6 raised to the 3 minus 1.2 power. If you want to put this all in the calculator at once, be sure that you have parentheses around that 3 minus 1.2 to indicate to your calculator that whole thing is in the exponent. Personally, I'd probably subtract those just so it's easier to type in my calculator and I'm not likely to make a mistake. So this is the same as 6 raised to the 1.8 power. Typing it into our calculator and rounding to the nearest hundredth, we get 25.16. Exponential functions and their graphs have several general properties. The first property is that the domain is all real numbers. Hopefully this makes sense. You've had lots of different numbers in exponents before, and it's never been a problem. We've had positive numbers, negative numbers, zero, fractions. There's never been a restriction on the number in an exponent, and there never will be. So our domain, all real numbers. The range, however, is only the positive numbers, 0 to infinity. Our base number b is defined to be strictly greater than 0 and not equal to 1. So this means that our base is a positive number. If you take a positive number and raise it to any power, you're still going to have a positive number. Therefore, our range is only positive numbers. The graphs of these exponential functions do not have an x-intercept. Since the range is only positive numbers and the x-intercept happens when y is equal to 0, this is never going to happen. In fact, there's a horizontal asymptote on the y-axis of these exponential functions. All exponential functions do have a y-intercept of 0, 1. Again, this should make sense to us since we're taking our base and raising it to the 0 power. We have an exponent rule that says anything raised to the 0 power is equal to 1. That's how we get the y-intercept of 0, 1. When b is greater than 1, the graph will rise from left to right. So it's going to look something like this. But if your base is some number between 0 and 1, the graph will fall from left to right. It's going to look something like this. And lastly, all exponential functions are one-to-one. We can see just by those little graphs I drew that they pass both the horizontal and vertical line tests. We have a special number when we start talking about exponential functions. The number e is called the natural base. E is an irrational number like pi that shows up all over in math and in nature. So e is approximately 2.72. The exponential function with base e, which is written f of x equals e to the x, is called the natural exponential function. This is such a popular function that you even have an e to the x button on your calculator. As I mentioned, e is an irrational number, which means it's a decimal that goes on forever, which is why we approximate it to be 2.72. And since f of x equals e to the x is simply an exponential function, all the properties that we discussed for exponential functions apply to the natural exponential function as well. Next, we'll be graphing exponential functions. Let's graph each exponential function, state the domain and range in interval notation, and identify any asymptotes. Our first function, f of x, is equal to 2 to the x. Well, when we first learn a new function, our graphing technique is to make an xy chart and then plot points. That's what we're going to do for all of these exponential functions. We know that the domain is all real numbers. So when choosing x values, we want to choose some negative, 0, and some positive. I recommend always choosing the x values -1, 0, 1, and 2. Exponential functions grow very rapidly, so you don't want too big of an x value or your graph is quickly going to go right off the paper. So let's find our corresponding y values. If we plug -1 in for x, that's 2 to the -1st power, which is 1/2. Plugging 0 in, 2 to the 0 power is 1. Plugging 1 in, 2 to the 1st is 2. And lastly, we have 2 to the 2nd, which is 4. So here are our 4 ordered pairs that we're going to plot. -1, 1/2, 0, 1, 1, 2, and 2, 4. All of our exponential functions have a horizontal asymptote on the y-axis. We'll draw that in. We know that these 4 points are going to connect, and we also know that one of the ends of our graph has to tend towards that horizontal asymptote. So which end do you think it's going to be? Well, the end on the left that's already really close to the asymptote. So this is going to continue extending, getting closer and closer to the x-axis, and the right end is going to continue up. So there is the graph of f of x equals 2 to the x. We want to state the domain, the range, and the equation of any asymptotes. The domain of all of our rational functions is -infinity to +infinity. We can also see that from our graph as we have an arrow pointing to the left and an arrow pointing to the right. The range, since we have that horizontal asymptote, our y values don't start until we're on the positive side of 0 and then extend to +infinity. Lastly, we want to identify the asymptote. We have a horizontal asymptote on the y-axis. So we say that we have a horizontal asymptote at y equals 0. Try another one. Let's graph f of x equals e to the x. Again, we're going to create an xy chart to get 4 points. Again, we're going to choose x values of -1, 0, 1, and 2. We'll plug these x values in and get our corresponding y value. Now, this is not one that we're going to be able to just do in our head. We definitely need our calculator for this. So you're going to be looking on your calculator for a button that says e to the x. Some calculators you have to put the x value in first and then the e to the x, and then other calculators you put the e to the x in first and then put in the exponent. So finding e to the negative first power, we're going to get 0.37. E raised to the 0 power will be 1. E to the first, 2.72. And then lastly, e squared, 7.39. Those are the 4 points that we are going to graph for f of x equals e to the x. Now we're just going to have to estimate when plotting these points since we have a bunch of decimals. So that's negative 1.37, 0, 1, 1, 2.73, and 2, 7.39. We know that there's a horizontal asymptote on the y-axis. And we also know that one end of our graph is going to have to tend towards that horizontal asymptote, and it's going to be the end that's already really close to the horizontal asymptote. Here's the graph of f of x equals e to the x. Please notice that this graph is a little steeper than the previous one. With e to the x, e is 2.72, so we have a larger base number in this example than the previous example. The larger the base is, the faster the graph grows. It's going to be steeper. Let's graph one more. You'll see that this equation has more to it. This is an exponential function that has transformations. Basically, all of our new exponential functions are a bunch of new parent functions that we can then graph by transformation. So let's graph each exponential function by transformation. We'll state the domain and range in interval notation, as well as identifying any asymptotes. Like anything that I graph by transformation, I like to start by outlining my plan. The first thing is going to be our parent function. The parent function is going to be an exponential function, some number raised to the x power. Our base in this example is 3, so our parent function is going to be 3 to the x. Something you need to note, since we're graphing by transformation, the exponent is considered the inside of the function. So you may want to put parentheses around it just to reinforce to yourself that that's the inside function. And now we start looking for our transformations in order. We always start with the inside of the function. There's only one thing happening inside our function other than the x, and that's a negative. Multiplication by negative on the inside of a function tells us that there's going to be a reflection about the y-axis. And when reflecting about the y-axis, we always multiply our x values by -1. Then we move outside the function and start looking for transformations. Now note, the 3 is part of the parent function. That is not a vertical expansion. That is part of the parent function. If there was a vertical expansion, you'd have to have something like 2 times 3 to the -x plus 1. It would have to be really obvious with parentheses around the 3 to the x or a multiplication dot as I've written it. So that 3, part of the parent function, not a transformation. The only other transformation we have is that +1 on the outside. And we know that +1 on the outside tells us that we need to shift our graph up 1. All right, let's get some points for our parent function. We're going to do so by making an XY chart. We're going to use the x values of -1, 0, 1, and 2 again. 3 to the negative first, that's 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. So those are the points for our parent function. Let's plot them. Remember that all of our parent exponential functions have a horizontal asymptote on the y-axis. And we'll plot our points. -1, 1/3, 0, 1, 1, 3, and 2, 9. And the end closest to our horizontal asymptote is going to tend towards that horizontal asymptote. There we go. There's the graph of f of x equals 3 to the x. We're ready for our first transformation. We're going to be reflecting about the y-axis. To get the points for this second graph, we're going to multiply all our green x values by -1. So that'll give us the points 1, 1/3, 0, 1, -1, 3, and -2, 9. Before I plot these points, I want to talk about what happens to our horizontal asymptote when we have a reflection about the y-axis. Does that asymptote move? Well, when reflecting about the y-axis, everything on the left side moves to the right, and everything on the right side moves to the left. So this left side of our horizontal asymptote is just going to flip over and be on the right side. Similarly, the right side of our horizontal asymptote is going to flip over and become the left side of the horizontal asymptote. The horizontal asymptote stays in the same spot. It's just kind of, flip-flopping on itself. Asymptote staying put. Let's plot those new points. 1, 1/3, 0, 1, -1, 3, and -2, 9. And there's our red graph. One more transformation to go. We need to take the red graph and shift it up 1 unit. To get the correct points for our final graph, we are going to be adding 1 to all the y values. So we'll have 1, 1 1/3, 0, 2, -1, 4, and -2, 10. Before plotting these points, let's talk again about our horizontal asymptote. If I'm shifting my whole graph up 1 unit, does the horizontal asymptote move too? That horizontal asymptote is a guideline for our graph. It tells us kind of where we need to stop. So yes, it does need to shift up 1 as well. If not, we would end up having extra space between our points and the horizontal asymptote. So our asymptote will shift up 1 unit as well. And then we'll plot our points. 1, 1 1/3, 0, 2, -1, 4, and -2, 10. And here we have our final answer in blue. The graph of f of x equals 3 to the negative x plus 1. We need to state the domain and the range, as well as the equation of our horizontal asymptote. So let's start with the domain. The domain of all exponential functions, no matter whether we have transformation involved or not, is -infinity to +infinity. And we can see that from our graph as we have an arrow pointing to the left as well as the right with no breaks in the middle. The range, well, since we have a horizontal asymptote and our graph is only above that horizontal asymptote, our range starts on the other side of +1 and goes to +infinity. Lastly, we want to state the equation of our horizontal asymptote. Remember that it shifted up 1, so now it's up here. So instead of being at y equals 0, it's now at y equals 1.